Nice to meet you. This is the Hobby IT channel. Thank you for watching today. In this channel, it is a video that challenges making things with IT. Programs and circuit diagrams are available on the website below, so please make use of them. Let's have fun together.
This time, I would like to work electronically about the infrared receiving sensor. We will implement the mechanism and usage of the infrared reception sensor, acquisition of remote control signals, etc. Let's start with the table of contents. Here is the table of contents. First, I would like to proceed from the overview, sensor mechanism, circuit diagram, wiring diagram, software, and operation check. Without further ado, I would like to move on to the next overview. This electronic work will eventually become a series of making a smart remote control, and will be distributed in a total of 7 videos. When completed, it can be operated from a smartphone, and we will realize home appliance operation from the outside and AI speaker cooperation. This is the third infrared reception sensor, and we will work on the hardware electronically and create the software. Finally, we will actually check the signal reception of the home appliance remote control. Move on. This item will be used. In particular, the receiving sensor implemented this time has a difference in sensitivity depending on the type, so please refer to the model number. Please note that the price is subject to change. Also, this list can be downloaded from the Hobby IT site overview. Move on. As for the development environment, we will use Arduino. It is widely used for learning all over the world, and there are many functions such as libraries provided, and there are many learning materials on the internet. It is easy to understand and easy to use, so I will continue to use it this time. Move on. We will understand the mechanism of the infrared receiving sensor. First, although infrared rays are invisible to the human eye, they are a type of electromagnetic wave, just like light. When this sensor receives an infrared ray, the volt terminal becomes low, that is, ground. High is output when there is no signal. It seems to be high when there is a signal and low when there is no signal, but this is how it works. Since the ESP32 3.3 volts terminal and ground terminal are connected to the VCC and ground terminals of the sensor, when the sensor is high, the voltage 3.3 volts input to VCC is output from vote. By the way, VCC is the input voltage for operating this sensor, and this sensor can be operated with voltages from 2.7 volts to 5.5 volts. The ESP32 receives the high and low signals output by vote of the sensor and acquires the infrared signal. Move on. Let's understand a little about remote control signals. Since the remote control signal is transmitted as a signal of 0 or 1, by changing the length of high or low of the infrared signal and transmitting it, 0 and 1 are distinguished and transmitted. There are several types, but in most cases, 1 is represented by making the length of high 3 times longer than that of 0, as shown in this figure. By changing the length of this high, it is transmitted as a remote control signal. Also, this is helpful, a typical remote control signal has the leader code first, followed by the data code. It seems that the home appliance judges whether it is the signal that it should receive by sending the model etc. with the reader code. This time, the content of the signal is irrelevant, but I thought it would be useful, so I introduced it. Move on. Here is the circuit diagram. It's very simple. The sensor has 3 terminals, and the 2 terminals of VCC and ground are power supplies for operation. The VCC terminal connects the 3.3 volts of the ESP32, and the ground terminal connects with the ground of the ESP32. Set IO23 of ESP32 to receive and get the signal from vote of the infrared receiving sensor. Move on. Here is the wiring diagram. We will add from the state where the previous LED was wired. This is because we will eventually produce a smart remote control. VCC is wired from 3.3 volts of ESP32. The ground is wired by extending it horizontally from the ground that was wired for the LED. As long as it's connected to the ground, it doesn't matter where the wiring starts, so I'll take the ground from the LED so that it doesn't have to be unnecessarily long. Finally, wire the IO23 and vote terminals. Now let's wire it up on the breadboard. Here are the parts that will be wired. It's running at 3x speed. First open the bag and take out the sensor. The legs are a little long, so cut them with nippers. Plug the sensor into the breadboard. Wire sideways from the LED ground. Measure the approximate length, bend it, and peel off the skin. Then plug it in. Measure, bend, and cut the 3.3 volts to approximate length. Now that it's cut, peel off the skin and insert it. Finally, wire the vote terminal to IO23. Measure, bend, and cut to approximate length as well. Peel off the skin and insert it. Insert so as not to touch the resistor. I've plugged it in, so I'm done. Now that the hardware is complete, let's create the software. The software used this time is posted on the Hobby IT site, so please use it. Understand the software. First, define IO23 that receives the signal from the infrared receiving sensor. Then the setup function begins. The setup function starts the serial monitor and sets IO23 reception. Since the connection terminal for the LED will be lit, it was set to output, but this time it will receive a signal, so it is set to input. Next is the loop function, where the IR receive function is executed in the if statement. Depending on the result, the content displayed on the serial monitor is changed. As a loop function, that's all, so I would like to understand the receive function of this IR. First, confirm what you want to achieve with the IR receive function. As you can see here, it means getting the length of time between on and off remote control signals. We will create a program to acquire this time. Move on. As shown in the top of this figure, the length of the signal is obtained by obtaining the elapsed time from the first starting point and subtracting the previous time to obtain the length of the signal. The reason why the starting point is used as a reference is that obtaining the length of the signal each time may accumulate errors, and we want to avoid discrepancies in the determination time. The bottom of the figure shows that the current change time is replaced with the previous time, and the length of the signal is obtained one after another. In addition, since it is not possible to determine whether the signal is at the end based on the change alone, if there is no change for half a second, it is determined that the signal has ended. Based on these, we will program. Here is the IR receive function. First, I understand the whole thing in the comments on the left side of the program. First, we declare the variables. Line 37 gets the current time in milliseconds. This is a system function that allows you to get the time in milliseconds since the system was started. After 15 seconds in the if statements on lines 55 to 57, exit the function and return the result as false or failure. The while statement on line 39 repeats the process. If the parenthesis of while is 1, the while statement itself loops infinitely. However, in this case, depending on the conditions, return will terminate the function itself with success or failure. The while statements from lines 43 to 58 are processed repeatedly until the next change in the infrared signal. In line 45 of this, it is judged whether there is a signal change for half a second. Here, if there is no signal change for half a second and the number of signals is 10 or more, the process ends normally. The number of signals in this program is the number of high and low transitions. The reason why it is set to 10 or more is that it changes in response to infrared rays that exist in the natural world, so if the number is less than 10 times, it is judged as noise. If it is 10 times or less, the counter is cleared once and the standby state is entered again. Next, lines 60 to 64 are executed when the first signal change is received. Holds the start time and increments the counter by 1. Next, from line 67 to line 73, the signal change is processed after the second time. Get the difference time from the last signal change and display it on the serial monitor. This makes it possible to obtain the length of time between with and without infrared signals. Now that you have checked the contents of the software, let's check the operation. First, write this software to ESP32. If writing does not go well, you have learned about writing in detail in the LED edition, so please check the contents once. The link of the LED edition is described in the summary column. When the writing is completed, operate the ESP32. Since the status cannot be confirmed as hardware, check whether the remote control signal is received with the serial monitor displayed. With the ESP32 in operation, point the remote control of the home appliance at the infrared receiving sensor and press the button. Keep a distance of 30 to 50 centimeters and lightly press the button only once. Conversely, some remote controls do not send a signal when pressed and held. Also, if you receive a lot of noise, close the curtains, move away from the window, or be unaffected by lighting. If the signal is received as shown on this monitor, it is successful. Noise may be mixed in, so please run it several times and check if you can get the same signal. This time it's a lighting made by Panasonic. Finally, save this acquired signal in an application such as Notepad, as it will be used in the next operation check of the infrared transmission LED. Then, I would like to finish the electronic work this time because I succeeded safely.
We will continue to take on the challenge of making things using IT like this, so please give us a high rating and subscribe to the channel. See you next time.